All right, we're doing vector diagrams. Let's get it. Hey guys, Mr. B here again, bringing another sweet, wicked, awesome physics video. In this video, I'm going to break down vector diagrams, how to do them, why they need them. We're going to solve some problems, and we're just going to get straight to it today. All right, guys, let's do it. Let's get into the screen. All right, so the first thing we're going to talk about, guys, if we're going to do vector diagrams and solve problems involving vectors, we need to kind of know what a vector is. So a vector is essentially a number with a direction. How much and where. So I'm just going to write that note really quickly. So it's a number with a direction. So in physics, we represent using notation always, right? So if we had a displacement, we would say, well, it's 2.5 meters. That's our number, 2.5. Now we need a direction to go along with it. So that might be north. Now, if it's a 2D vector, maybe it has a little bit more of a complicated direction. Maybe it's 2.5 meters, 25 degrees north of east. So that's what we're going to kind of tackle today. When we have these 2D vectors, so when 2D vectors get created from, going in at an angle, or if you have one vector going, say, north and the other one going east, and then you get a resultant, which is what we're going to do. So we're going to do that in a problem-solving situation where we have to make a vector diagram. So first thing we need to do is we got to be able to know the autonomy of an arrow. So every arrow has a tail and it has a tip. So this is your tail over here, and that's the beginning. When we draw our arrow, we always draw the tail first. And then, of course, the tip is the arrowhead. And the length of the arrow, so the length equals the magnitude. So remember the word magnitude. If you don't remember it, you might want to go back and watch my video on scalar versus vector. Drop that in the description. Magnitude means the size. So 5 meters, 20 meters. So the length of the arrow corresponds directly to that. So if we have two arrows, one is 5 and one is 10, then that means that the 10 is going to be twice as big as the 5, just like the number is. Now, the key when drawing vectors is to do tip to tail. So we never draw two arrowheads together. We always draw the tail of one touching the tip of the other. And we'll see that now when we do a little question. So let's try that. All right, so here we got a problem that says a student drives their car 9 kilometers per hour north. So let's make note of that number, 9 kilometers per hour, or 9 kilometers north, not per hour. Before making a right-hand turn and traveling 7 kilometers per hour east. So there we go, 7 kilometers to the east, not per hour. I keep saying that. 7 kilometers to the east. What is the displacement of the student? Draw a vector diagram. So let's go ahead and set up a simple little compass heading here that I'll just switch my color now to blue. So we're going to go 9 kilometers north first. So north, east, south, and west. Never eat soggy waffles. And then we go north 9 kilometers. So that's our starting point. And we went our D1, which is 9. So let's write D1 down here equals 9 kilometers north. So we know that 9 is a bigger number than 7. So our arrow for the 9 should be slightly longer than that of the 7. Again, we're not measuring it. We're just kind of guesstimating it as best as we possibly can. So there we go ahead. We do that. And now I'm just going to dot this arrow in here. So that is the result of doing that. So our resultant displacement. So remember, displacement is distance from starting position. So we started down here at this dot, and then we ended up over here. I'm going to draw my rocket car. Eat your heart out, Elon. I've been drawing those since I was a kid. And we'll write in our D2, which is 7 kilometers east. So those are our two vectors that we drew in our vector diagram. And now we're going to use trig to be able to get the resultant displacement. So we've got to go ahead, we'll put our theta in here, just like that. And now we're going to go ahead and find the two things that we need for a vector, which is the magnitude and direction. So let's go ahead and do the magnitude first. So the magnitude. Now, when I drew my vector diagram, I put, variables essentially on them. So I labeled D1, D2, and DR. Some teachers might say to put the numbers there. It's up to you. I tell my students to put the variables there just because we want to keep it sort of consistent with what we would do if we were doing a vector diagram for relative velocity, which is coming, right? So we'll do our Pythagorean theorem. So for every right triangle, we can use Pythagorean theorem to find the hypotenuse. So that's our go-to. So c squared equals a squared plus b squared, but we'll do it in terms of our triangle, which is the resultant displacement is the square of d1 and d2. I try to remember to put my arrows on top of stuff, guys, but to be honest with you, when you're in the heat of a moment doing a question, I never take marks off if my students don't do it. So usually final answer, that's a good benchmark. So we'll do our dr squared, and we'll go ahead and put our 9 in for d1, and then our 7 in for d2. So 9 squared plus 7 squared, so that's 81 plus 49. That's going to be 130. So dr squared equals 130. Now we'll go ahead, we'll take the square root of that. So the square root of 130, somewhere in the neighborhood of 11.4 kilometers. And if I mess that up, my mental math, then you guys can drop it right in the comments and correct me. I make a lot of mistakes, so I wouldn't doubt if I mess it up. So that's the magnitude, 11.4 kilometers. Now we can kind of put that back down to 11 if we're using significant figures. 130 only has 2 sig figs. So now we got to get the direction. That's the magnitude of it. So now we'll do the direction of it. And I think that's kind of the part that I want you guys to really connect. It seems like the idea that vectors is just something so simple. It's a number and a direction, yeah, but this applies to more difficult situations like this one, and then eventually more when relative velocity happens. So when we're going to find the direction, it involves finding the angle. So we want to use right angle trig, or SOHCAHTOA, sine, cos, tan. Now we have all three sides of the triangle now that we have the 11.4 for the hypotenuse. However, I wouldn't use the 11.4. I definitely wouldn't use the 11. But if you were going to use it, use the 11.4. And you could use sine and cos because that's the hypotenuse side. But I would prefer you guys to use tan. So tan theta is opposite over adjacent. So I'm just going to kind of redraw this triangle out here for a second. Here's the triangle that we have. Just like that. And we end up with this being our theta. So this is our adjacent side, not the opposite. This is the opposite. And this is the hypotenuse. So we have the A and we have the O, which is 7 and 9. So we'll go ahead, we'll use our inverse trigonometric function to find an angle, so tan negative 1. And then we'll put our opposite side in, which is D2, which is 7. And then our adjacent side, which is 9. Just like that. And you could fill the numbers in this one if you wanted to make life easier on yourself. Like, if you feel like you want to do that. There's a lot of ways to do this, but I think if you've reached this point in physics that you're doing this, that you could probably look at this and be able to just go ahead and put the numbers in. But again, you got to judge yourself and do it as what's best for you. So I think that's somewhere in the neighborhood of 40. I'm not confident in that, though. So I'm just going to double check my calculator, which is 38, so pretty close, 38 degrees, just like that. So now that we have the actual degrees, we want to go ahead and see if we can't find the compass direction. So 38 degrees, what of what? So what I like to do is I like to think about what vector did we go on first. So we went on the north vector, and if I were to draw a little arrow that goes from the north vector to my result, I went to the east to get to that vector. In fact, I went east of that north vector, right? So that's my compass heading. east of north. Now, there's another way to kind of do it that works really well. This is more of just a hack. You don't really need to understand anything, but if you look at what we did here, we did 7 over 9. So that's east over north. So if you go east over north, the east vector divided by the north vector, then you can get your compass heading really easy, just east of north. So now we can write our final answer, and I'm just going to move my head over here a little bit. Woo! And then we end up with our final answer. Oops, didn't mean to do that. dr equals 11 kilometers, 38 degrees, east of north. All right, guys. Hopefully this video helped you in some small way. If it did, I really appreciate it. And thanks for watching. Thanks for sticking around. If you got any questions, feel free to drop a comment. Thank you guys so much, and I will see you guys in class. Peace.